State-of-the-art quantum computers currently require massive cryogenic cooling systems to function, but researchers are working to shrink that processing power down to a monolithic chip no larger than a single penny. Silicon microchips face a hard scaling limit because they generate heat through the physical movement of electrical charge. Forcing electrons through nanoscale wires creates Joule heating, which wastes energy and damages delicate components. Quantum processors are even more sensitive. To prevent thermal noise from destroying qubit states, engineers must build large, complex physical resonators to connect them. For quantum computers to become practical, they need a quantum bus, a stable data pathway linking hundreds of qubits together on a high-density chip. The path forward requires a transmission mechanism that avoids moving physical charge entirely. One candidate is the Magnon. A Magnon is a quantized spin wave, a wave of magnetization that travels through a solid magnetic lattice. Because the atoms in the lattice do not change position, information moves without the electrical friction that plagues silicon. Furthermore, Magnon wavelengths naturally shrink to the nanometer range, allowing them to fit into the same high-density architectures used in modern smartphones. Until this study, the lifespan of a Magnon, the duration it can reliably carry information, was limited to a few hundred nanoseconds. This presented a major technical hurdle, as a quantum logic gate typically requires several microseconds to successfully execute a coupling transfer. A nanosecond lifespan is essentially a dropped signal, cutting off data transmission before a quantum calculation can finish. A research team at the University of Vienna, led by Professor Andrii Chumak, has developed a method to overcome this dissipation limit, recently publishing their results in the journal Science Advances. The team demonstrated Magnon lifetimes of 18 microseconds, a 100-fold increase over previous observations. Their first strategy involved exciting short wavelength Magnons. Unlike uniform Magnons, which tend to dissipate when colliding with defects on the crystal surface, these shorter waves travel through the center of the material, avoiding the edges. The researchers also isolated ultra-pure spheres of yttrium iron garnet, or YIG, a magnetic insulator known for low spin wave damping. They placed these YIG spheres inside a mixed-phase cryostat and cooled the system to 30 millikelvin. At this extreme temperature, just a fraction of a degree above absolute zero, the thermal processes that normally disrupt Magnons are effectively frozen. The team's results show that Magnon decay is a consequence of material impurities and experimental geometry, rather than an immutable physical law. Testing YIG spheres of varying purity revealed a massive damping peak at 50 Kelvin in lower purity samples, caused by trace rare earth ions siphoning energy. In the ultra-pure sample, this peak disappears entirely, ensuring a stable, low-loss environment down to millikelvin temperatures. Notably, even the least pure sample in this experiment outperformed the best historical records for Magnon longevity. These results suggest that achieving millisecond-scale coherence is now a matter of materials engineering rather than theoretical discovery. While bulk spheres are ideal for laboratory testing, scalable quantum processors require planar, thin-film architectures that can be integrated onto a chip. Paramagnetic GGG substrates generate stray fields that penetrate the YIG film, causing severe distortion at cryogenic temperatures. Scientists solved this with YSGAG, a diamagnetic substrate that remains magnetically neutral even at 30 millikelvin, providing a stable foundation for low damping. Using these clean films, researchers can now employ inverse design AI algorithms to autonomously sculpt nanoscale logic gates directly into the magnetic layer. Combining these diamagnetic substrates with algorithmic design creates the physical architecture needed for scalable, planar networks on a single chip. An 18 microsecond lifespan brings Magnons into parity with the coherence times of leading superconducting qubits. This allows Magnons to serve as universal translators within a hybrid architecture, bridging different quantum systems like optical resonators and acoustic phonons. This shared pathway functions as a quantum bus, providing the stability to connect hundreds of qubits along a single microconduit. Because Magnons possess nanometer wavelengths, these circuits are orders of magnitude smaller than photon-based systems. By increasing Magnon lifetimes 100-fold, researchers identified a hardware route to condense a quantum computer onto a chip the size of a single penny.